All right, welcome everyone to the second session of Science at Low Frequencies, the 7th installment. We have a fantastic set of talks coming up on the topics of fast radio bursts and pulsars. I wanted, and I think Joe agreed to this as well, to just for 1 minute maybe pay our condolences to the Arecibo telescope, which if you have been watching the news or Slack, collapsed last night. So Arecibo, of course, has been an iconic radio telescope for half a century already. I think quite fitting for this session, for instance, was the telescope with which the first repeating FRB was actually discovered back in 2016. And like I said in Slack, I think it's the mother of many radio astronomers out there. A lot of people who started their career using Arecibo or were inspired to go into radio astronomy in the first place because of Arecibo. I, for instance, saw Arecibo in Contact when I was in high school, and I thought, no, I think I should become a radio astronomer instead of going into medicine. Yeah, so I'm not sure I have too much more to say about it. Could talk about it for a very long time, but I just wanted to take one moment to pay our respects. All right, so let's transition to more positive things. And let me find my window again where I have my schedule. So like I said, welcome to the second session on FRBs and pulsars. We're starting the session with an invited talk by Pragya Chawla from McGill University in Canada. And she's going to be talking about fast radio bursts and their low frequency emission. Maybe I'll ask you, Pragya, to share your screen. And while you're doing that, I'll remind people that if they have questions during the talk, you can put them in the Q&A. And I can also unmute you in case you want to ask your question out loud. Pragya, you have 25 minutes plus 5 minutes for question. And yeah, if you're starting to hit the end, I'll maybe give you a short warning. Right.
Sure, sounds good.
Take it away, Pragya.
Thanks. Yeah. So hello, everyone. Today I'll be talking about fast radio bursts, reviewing the state of the field, while specifically focusing on the search and detection of emission of at low frequencies from these bursts. So let's jump right in. Fast radio bursts are millisecond duration events that have been detected using their radio emission. So the first burst was detected in the year 2006, and the detection plot is shown on the right. So frequency is on the y-axis here with time on the x-axis. And as you can see, the higher frequencies arrive earlier than lower frequencies, and this delay is quantized by the dispersion measure. Physically, the dispersion measure corresponds to the integrated electron density along the line of sight from the source to the observer. And the most important property of FRBs is that their dispersion measures are in excess of what was expected from the models of electron density in the Milky Way galaxy, implying that these bursts are located at extragalactic or cosmological distances. So there are about 120 FRBs known today, and given the small field of view of radio telescopes that were used to discover these bursts, the inferred all-sky rate is about 600 FRBs per day above a flux density of 1 Jansky. And most of these FRBs in the initial days were followed up for hours with other radio telescopes, and the bursts were not detected to repeat. But now we know that some FRBs do repeat. The first repeat bursts were detected from FRB 121102 with the Arecibo telescope, as Jason just mentioned. And the plots that are shown here are some of the repeat bursts from FRB 121102. And these bursts are now corrected for the dispersion. So the spectrum here looks like the burst has arrived all at the same time because the dispersion has been corrected for. And another curious thing to note is that the spectrum seems to vary between repeat bursts. So some of these bursts have rising spectra, some of them have falling spectra. And these bursts, some of them have been detected within minutes of each other. So now, in the year since the detection of the first repeat burst in 2016, we now know about 21 repeating FRB sources. And at least we can rule out the cataclysmic models for these sources. However, we still don't know what causes fast radio bursts. So there are about 50 proposed models out there in the literature, and the millisecond duration timescales imply that most of these models invoke that compact objects are the origin of fast radio bursts. The models range from pulses from young neutron stars to flaring magnetars to mergers of compact objects. 13 fast radio bursts have been associated to their host galaxies that have allowed in the determination of their galaxy properties. So the plot here on the right shows the properties of some of the localized galaxies of fast radio bursts and their star formation rates on the y-axis and the stellar mass on the x-axis. And as you can see, the galaxy types still don't yet hint at a particular progenitor. So here in this plot, like the different boxes correspond to what phase space different progenitor models would occupy. And as you can see, the points here that are associated with all of the FRBs are all over the place. So we need more localizations to be able to say something about what progenitor models a large fraction of the FRB population is coming from. However, there were some discoveries this year that are starting to give us more clues about what FRBs could be. And earlier at the start of this year, 2 of the repeating fast radio bursts were found to be periodically active. The first of these was FRB 2018-0916b, discovered by the CHIME FRB collaboration. And this source was found to be periodically active with a 16-day modulation in its activity, having 5-day long activity periods. So the plot here, the black markers show the exposure that the CHIME telescope had to the source, and in red are marked the times where bursts were detected from the source. And as you can see, all of these bursts were detected within these gray regions, so within the activity periods of the source, despite there being considerable exposure outside the activity regions. And shortly after, a potential periodicity was also detected in FRB 121102, so the first repeating fast radio burst, except this time the activity period was much longer, so about 157 days, having a much larger duty cycle as well, so about 50%. The plot here shows the similar timeline for FRB 121102, except that the active regions are now marked with these, are now shaded with yellow. And all of the FRB detections are shown by these markers here. And the discovery of periodic activity in 2 repeating FRBs can point us to a lot of different progenitor models. So the periodicity could be due to orbital motion. Say, for example, if a neutron star is in orbit around another star and the star is only emitting at some phase of the orbit, then you could expect to see this periodicity. Other models include rotation and precession. The rotation is a bit hard to achieve because it's hard to get, say, magnetars to rotate on weeks or months time scale. We usually know magnetars that have seconds, that have rotation periods around the order of seconds. So that's a bit hard, but these are some of the explanations that are still out there and could be able to explain the periodic activity in these sources. The other main discovery this year was that we detected a fast radio burst from a magnetar in our own galaxy. So this burst was detected from magnetar SDR 1935 plus 2154 with 2 different radio telescopes. So with CHIME at a frequency of 600 megahertz and with the STARE-2 radio array at a frequency of 1.4 gigahertz. So the 2 plots are shown here, and the STARE-2 burst is likely associated with the second component here of the CHIME FRB detection. While this burst was not as energetic as an active FRB, it was over 1,000 times brighter than any burst from a radio magnetar in our own galaxy. So it reduces the energy gap between magnetar bursts in our own galaxy and fast radio bursts and suggests that at least some FRBs could be magnetars. Now let's switch to some other properties of fast radio bursts that will allow us to use them as cosmological probes once we discover more FRBs that have host galaxy associations and hence their redshifts determined. So the most important property there is dispersion, where the dispersion measure of any FRB encodes contributions from the Milky Way, the intergalactic medium, and the host galaxy. Once we can plot each of these FRBs in the DM redshift space, as has been done for FRBs localized with ASCAP here, denoted by the colored markers. And once we have this DM redshift relation, known as the McQuart relation, this can allow us to get an independent measurement of the cosmic baryon density, because the mean of this relation depends on the baryon density. And the initial results, based on the detection of 5 bursts with ASCAP, are consistent with CMB experiments, although the fractional errors are of the order of 50%, so the uncertainties are large due to the small sample of bursts. But it goes on to show that once a lot of FRBs are localized and have their redshifts determined, we would be able to perform this science with much lower errors. The other important property of fast radio bursts is polarization, and that will allow us to study the magnetic fields along different lines of sight in the universe. And 19 fast radio bursts have measured rotation measures. While for most of them, the rotation measures are less than 500 radians per meter square, so they could be consistent with magnetic fields in the Milky Way, so the rotation measures that we see for, say, pulsars in the Milky Way. However, one source, so the first repeating FRB, 121102, has a rotation measure that is 10 raised power 5 radians per meter square, and it is 100% linearly polarized. So the plot shown here shows the Faraday rotation, so the Stokes Q and Stokes U parameters as a function of frequency, and the line that is fit to these data points in black is what corresponds to this rotation measurement of 100,000 radians per meter square. The polarization fractions are more of a mixed bag. So the linear polarization fractions range from 0 to 100%, and the circular polarization fractions range from 0 to 30%. But it goes on to show that once we have a lot of FRBs that have measured rotation measures, we can really study magnetization along different lines of sight in the universe. Let's now move on to the frequency dependence of FRB emission. So this is how the FRB detection landscape looked like in January 2018, after a decade of FRB searches. So in the initial days, most of the detections were made with the Parkes telescope, and hence most detections were at 1.4 gigahertz. There were searches that were conducted at lower frequencies that did not yield many detections because no FRB emission was found below a frequency of 700 megahertz. So this changed once the Canadian Hydrogen Intensity Mapping Experiment, the CHIME telescope, came online. This is the same plot now, but on January 2019, so a year after the previous plot. And that is when CHIME had started to detect bursts. So we saw FRBs having emission at 600 megahertz, with some of them showing emission even up to 400 megahertz. So these are the detection plots of the first 13 fast radio bursts that were detected with CHIME. And these are all corrected for their dispersion. And as you can see, a lot of these bursts show emission up to 400 megahertz. So just to give a brief overview of what the CHIME telescope is. It comprises of 4 cylinders that are 100 meters in length and are aligned along the north-south direction. It observes between 400 to 800 megahertz. It was designed to do hydrogen intensity mapping, to map the expansion of the universe, but it is now also being used to study fast radio bursts and pulsars. Its field of view is very large, so 120 degrees in the north-south direction, and varying between 1.3 to 2.6 degrees in the east-west direction. And this large field of view allows the instrument to have a very high detection rate. So if you now focus on the plot on the right here, that has observing frequency on the y-axis and the instrumental detection rate per day on the x-axis. In green are all of the telescopes that have detected FRBs. In red are the ones that have not detected FRBs so far. And as you can see, CHIME sits on the far right of this plot, having the highest detection rate of all FRB detection instruments. Another key property of CHIME is that it is a transit telescope. So it revisits every location in the northern sky every single day, and is thus ideal for detecting repeating FRB sources. So 18 of the 21 repeating sources were detected by CHIME, and we are continuing to detect many more. So the state of the field now, so this is say the same plot, but on July 2019, so after the first year of operations of CHIME FRB, and we have now discovered over 500 bursts, thus greatly expanding the population of FRBs detected at frequencies lower than 1.4 gigahertz. And the next talk would be by Ziggy Plunis, who will be describing the properties of this catalog further. But following the detection of so many of these bursts at 600 megahertz and having emission up to 400 megahertz, there were renewed efforts to follow up FRB sources at lower frequencies, which resulted in the detection of FRB 2018-0916B at 300 megahertz. Remember, this is the first FRB which was detected to have a periodicity. So the source was followed up with the Green Bank telescope and the Sardinia radio telescope at 350 megahertz. And the observations were scheduled within the activity periods of the source, which made the source easier to follow up and detect bursts from these sources. So 7 bursts were detected with the Green Bank telescope, and these are now the dynamic spectra of all of these bursts. And as you can see, there is emission that is detectable up to 300 megahertz in all of these bursts. It was the same case for the Sardinia radio telescope, which had 3 detections of the same source in its activity period. And both these observations combined tell us that the spectral cutoff or turnover for FRB emission exists below a frequency of 300 megahertz. So the observations that were done with the Green Bank telescope also had coverage simultaneously with LOFAR and CHIME. So the source was being followed up in 3 frequency bands, but there was only one simultaneous detection with GBT and CHIME. And none of the other bursts was detected simultaneously between the 2 instruments. And there were no bursts that were detected with LOFAR between 110 to 190 megahertz, despite exposure for 6 of the GBT bursts. So one of the explanations for this could be that FRB emission is band limited, and the lack of more simultaneous detections, even between GBT and CHIME, suggests that FRBs could have a variable overall spectrum with individual bursts having different frequencies, and this frequency, the emission frequency, just varying with time. So the plot here shows the one simultaneous detection that we did get with GBT and CHIME. So this is the brightest burst here. And we saw the burst in 100 megahertz in the CHIME band, not seeing it in the rest of the CHIME band. So no emission was visible between 500 to 800 megahertz. And then the burst drifted into the GBT band, which is a common characteristic of that we have seen for repeating fast radio bursts, this frequency drift where the center of the emission frequency changes or reduces with time. So later this year, the first FRB was also detected with an all-sky survey below 400 megahertz. So this detection was made with the Green Bank Northern Celestial Cap Pulsar survey. And the survey has been studying the entire northern sky with the Green Bank telescope in the frequency range of 300 to 400 megahertz with about 2-minute pointings at each of the locations that are marked here. And it detected its first FRB, although with marginal signal to noise, about 8.4. But the detection of one FRB in the observing time of this survey can allow us to determine an all-sky FRB rate at 350 megahertz. So the rate, like right now, sits at about 3,000 FRBs per sky per day above a flux density of 0.4 Jansky. since this is just based on the detection of one burst, the Poissonian uncertainties are large. So you can see the entire range here on this plot. This shows the frequency as a function of rate. So the frequency, the rate measurements at different frequencies are shown here. This is the rate that was determined with the Park surveys at L-band. This is the rate from the Atmos surveys. The red marker here is from the CHIME FRB collaboration, the rate floor. So we are still working on quantifying the selection function and have an actual rate measurement, but we know that the rate is higher than this. And at 350 megahertz, there is still a large range of allowed rates, but we are hoping that more detections in low frequency sky surveys can allow for better constraints on the rate in the near future. But the picture that now seems to emerge is that FRBs have been detected at frequencies above 300 megahertz, but there have been surveys done with LOFAR and the Murchison-White field array that have not detected any FRBs below a frequency of 300 megahertz. And there could be potential explanations for this low frequency dearth, starting with an intrinsic spectral index. So say if FRBs were intrinsically fainter at low frequencies, you would not expect to see them with these surveys. So a lot of these surveys have compared the upper limits that they derive on the FRB rates based on their non-detections with the FRB rates that are determined at higher frequencies, so at 1.4 gigahertz, and comparing these two to derive a constraint on the spectral index of FRBs. So the constraints that they derive suggest that FRBs need to have a fairly positive spectrum, so a spectrum that rises with frequency, to be able to explain the low frequency non-detection. However, all of these constraints are in tension with the measurement from ASCAP. So the FRBs that ASCAP has detected, if you combine all of their spectra to have a mean FRB spectrum, the spectral index for that mean FRB spectrum is negative and is in tension with all of these constraints. So this issue can be resolved if instead FRBs were being rendered undetectable at low frequencies due to a spectral turnover rather than an intrinsic spectral index that's positive. So this spectral turnover could arise due to, say, free absorption in the medium or induced Compton scattering, and could render the FRBs undetectable at frequencies below 300 megahertz. The other explanation that could be possible for this low frequency dearth is scattering in the intervening medium. So FRBs undergo, similar to pulsars, undergo this phenomenon of scattering, where FRB signals take multiple paths in the intervening inhomogeneous plasma. And these different signals then arrive with successive delays. So a pulse with a sharp rise and a sharp fall instead gets exponentially broadened. And this tail then has a frequency to the power -4 dependence. So you'd expect these tails to be broader at lower frequencies, as is shown here for an FRB that was detected with Parks. What this does is that it reduces the detectability of FRBs at low frequencies because it reduces the peak flux that makes it harder for the search pipelines to be able to detect these bursts. And this is shown in the plot here on the right that has scattering time on the y-axis and dispersion measure on the x-axis. The black markers here are pulsars in our own galaxy. In blue are the FRBs that have been detected at 1.4 gigahertz, and in red are the FRBs that have been detected at 600 megahertz. And as you can see, the FRBs that have been detected at lower frequencies seem to be underscattered as compared to the FRBs detected at higher frequencies, suggesting that there are selection biases that we have against detecting highly scattered bursts at lower frequencies. So all of these effects that could cause FRBs to be undetectable at lower frequencies also motivates us to search for these sources at low frequencies, because they can allow us to constrain emission mechanisms and progenitor models based on the detection or non-detection of FRBs at low frequencies. So say once we know the cutoff or the turnover frequency of FRB emission, that can allow us to place constraints on free absorption in the surrounding media. As an example, the detection of FRB 2018-0916b at 300 megahertz ruled out its association with a hypercompact H2 region or a young supernova remnant. And the rationale behind that was that since we know that the surrounding medium is optically thin to free absorption at 300 megahertz, and once you combine that with constraints on the dispersion measure, you can place a limit on the size of the surrounding nebula being greater than 0.02 parsec, therefore ruling out such hypercompact progenitor regions. Searches at lower frequencies can also allow us to determine the properties of circumburst environments. So say if we know what the mean FRB spectrum looks like, and assuming it peaks at 500 megahertz, we can actually place constraints on the electron densities and electron temperatures in the medium surrounding the FRB. So this plot assumes that the FRB spectra peaks at 500 megahertz, and they're like knowing that, say, the environment surrounding FRBs is optically thick to free absorption at 500 megahertz. You can actually rule out the part of this the parameter space that's shown here in green. So you can rule out regions of electron density and high electron temperatures just based off of where the FRB spectra peaks at. So once we've established that searches at lower frequencies can result in interesting constraints on emission mechanisms and progenitor environments, there are a lot of searches that are being conducted to search for these sources at frequencies lower than 300 megahertz. Detections in blind surveys are crucial to understand population statistics and average spectrum, as well as for determining the FRB rates. But targeted searches could yield detections at lower frequencies on a much shorter time scale. So one of the ways to do this is with follow-up observations of repeating FRBs. Notably, this has been done for FRB 121102 and FRB 2018-0916B, the two periodic FRBs with low FAR at 150 megahertz, but no bursts were detected. However, we could selectively choose FRB sources that say have a high repetition rate or a low scattering time scale, or are located outside the galactic plane, and follow up these sources at lower frequencies to be able to detect low frequency emission from FRBs earlier than these FRBs would show up in blind surveys. Other techniques that are being used are doing shadowing observations or triggering observations on high frequency FRBs. So the Aptiv system on the Westerbork telescope is planning to trigger low FAR once they detect an FRB at a higher frequency to be able to detect the low frequency emission from the same source. And this was done for the 7 ASCAP FRBs, whose observations were shadowed with MWA. However, these FRBs were not detected at below 200 megahertz with the MWA. And it could be that there is a spectral turnover at 200 megahertz, or the detection could be because of the band limited nature of the emission. So if the FRBs were narrow banded enough to show up at 1.4 gigahertz and not show up at 200 megahertz, the detection of these FRBs with ASCAP and the non-detection of these FRBs with MWA could still be explained by the band limited nature.
Pragya?
Yes?
A couple of minutes.
Okay, yeah. Okay, so now, like going forward, we probably need to think more about trying to adapt our search strategies to different burst morphologies. So all of the low frequency surveys whose constraints I reported previously were searching for band averaged emission from these bursts, so integrating over the entire bandwidth. But as we know, FRB emission can be band limited. So maybe we want to start thinking about searching for narrow banded bursts. So we could search different frequency subbands separately. Or we could also search for these drifting subbursts. So these bursts were first noted for FRB 121102, where the emission frequency drifts downwards in time. We could adapt our search pipelines to look specifically for these bursts to increase the chances of detecting these bursts at lower frequencies. And similarly, we could also target the highly scattered bursts if we expect that we are missing a large fraction of the population because of their high scattering. So I leave you with a summary. FRB emission does exist up to 300 megahertz, and searches at lower frequencies will likely yield detections in the future, but we require complementary strategies of both targeted searches and blind surveys to fully understand the FRB spectrum. But yeah, that's all from me.
I'm sure I'm not the only person clapping, but I'm the only person you can hear clapping. Thank you very much for that excellent talk, Pragya. We have a number of questions. I'm going to read them out loud for the sake of expediency. So Pranav has the question, do we have enough observations to get totally convinced that the radio bursts are repeating?
Yes, so we do have, say, about like 20 sources that we know are repeating. And these sources, some of them have say repetition at a different cadence. So some of the sources are repeating on weeks time scales. Other sources are repeating on months time scales. And there have been thousands of bursts detected from FRB 121102. So I'm just showing the first 5 bursts here. So we are pretty convinced that these sources are repeating.
Yeah, I think it's pretty well established, but we don't know whether all FRBs are capable of repeating. Yeah.
Yes, that's correct. Like there is a large range in the repetition rates across sources. So like as of now, we really can't say anything whether the one-off bursts are really one-off bursts or we are just waiting for a detection from them.
Yeah. Okay, we also have a question from Magundan. Any comments on the detection of a few FRBs at 111 megahertz by the BSA? This is a Russian telescope in Pushino, I believe.
Yeah. So I do remember looking at those plots. The main issue there is that they have a very narrow band. So it's hard with the narrow bandwidths to be able to distinguish between RFI and astrophysical signals. So yeah, like those are tentative detections at this point, but have not been confirmed with any other telescopes.
Great, thanks. Jean-Matthias, I think is more of a comment than a question. He just says test. Okay, I'm assuming that's just a comment. Let me ask a question as well, and maybe other people can type in questions while I'm asking this. So I was wondering, does it seem to you, like in your experience so far, that maybe some FRBs are more easily visible at high frequencies versus low frequencies? Is there kind of like a preferred frequency for certain FRBs?
Yes, it has been suggested in the literature, at least for FRB like 121102, it seems like it's more like the detection rates are higher at higher frequencies, while say for FRB 2018-0916b, the detection rates seem to be higher at lower frequencies. So there could be preferred regions of emission for different FRBs. It's just that we don't have say a statistical sample for a lot of these sources. Mm-hmm. Like the non-detections are sometimes not reported in the literature. So there is no combined, like say, meta-analysis of like how different FRBs have their rates varying as a function of frequency. But it like at this point, it's like hints are starting to emerge that there are preferred regions or preferred frequency regions where some FRBs emit at. Great.
Yeah, I have lots of questions about what that might mean. I don't think we have time to ask them all. So let's thank. Oh, there might be one last question. Oh, it's more of a comment. So I will leave that in the Q&A for other people to read, because I think we're running a little bit low on time at this point. So let's thank Pragya again. I'm sure everyone is clapping wherever they are in the world right now. And let's move on to the next talk, which will be given by Ziggy Pleunis. We'll be talking about fast radio burst morphology and the first CHIME FRB catalog. And Ziggy is also from McGill University.
Can you hear me all right?
Yes, can hear you fine. So Ziggy, you have 17 minutes plus 3 minutes for questions.
Okay, thank you. So yeah, I'd like to delve a little bit deeper into fast radio burst morphology in the CHIME catalog. So here on the title slide is a glorious shot of CHIME again that Pragya already introduced. So fast radio burst morphology, what I'm talking about then is the dynamic spectra of fast radio burst and total intensity. So all of these figures that I'll be showing here are frequency on the vertical axis and then time on the horizontal axis. And in all cases for these FRBs, the dispersion delay has been removed. So the structures have been lined up. And already in this, there's a little zoo of fast radio bursts at very high time resolution. You can see a wide variety of morphologies. So you see bursts that extend full bands, and on the right you see bursts that drift down in frequency, as Pragya already introduced. And it's interesting to study these morphologies because they are shaped by an unknown or as of yet unknown emission mechanism of these bursts, and they can tell us something about that. And then as the FRBs travel towards us, they're also transformed by the propagation through the ionized and inhomogeneous medium. So from studying the burst morphology, we can get constraints on scattering, scintillation, etc. And the other interesting thing with morphology is you can already see here, different FRBs look different in terms of their morphology, and that might be a way of classifying them. And Parga already alluded to a lot of the repeating bursts showing downward drifting subbursts. And indeed here, the 3 bursts on the right are from repeating sources, and the 3 bursts on the left so far have not yet repeated. So we might use morphology as a way of classifying different populations of FRBs. And we already know from the early CHIME sample that repeater bursts and one-off FRBs have different observed width distributions. We showed this in the papers where we announced the new repeating sources, but this was a limited sample. And on the left, you can see we compare the pulse widths of the non-repeating bursts in the blue hatched region with the widths of the repeating bursts in orange. And these were just 12 non-repeating bursts and then bursts from 18 different repeaters. And we're now gearing up towards this catalog that Parga mentioned. And this will give us a much larger sample to redo the same analysis. So this first catalog of CHIME fast radio burst, it will contain about 500 non-repeating FRBs and then 16 repeater bursts that have already been published in these original announcements of these sources. And this is about a year of data from 2018 July to 2019 July. And we calculate the exposure to all of these sources and the sensitivity of the telescope. And we will also provide localizations and a rate estimate based on this information and a log n log s distribution, or at least an estimate of that. And then we're working on these accompanying analysis. And today I'll be discussing just the burst morphology based on this sample in the catalog. If you consider all of these 500 or so fast radio bursts in the catalog and you just look at all of their dynamic spectra, you can roughly identify 4 fast radio burst archetypes. So going from left to right here, so this is all in the CHIME band using total intensity data at 1 millisecond time resolution. So from left to right, you have the bursts that are broadband. They extend all the way from 800 megahertz down to 400 megahertz, and they just show one peak, might be scattered, as you can see here, scattered broadened towards lower frequencies. Then there's bursts that show up just narrow banded with one peak. You have bursts that show multiple peaks. And then on the right, I'm showing one example of one of those downward drifting subbursts. And I put the relative percentages by which they appear on the waterfall plots. And one thing you have to be wary of in doing this kind of analysis is the instrumental effects, because there are multiple ways in which the instrumental parameters can make your observed morphology different than the morphology of the burst on the sky. So for example, because the chromatic effects in the beam response, if you're outside of the main lobe of the radio beams, you might detect something that's narrowband that's actually broadband on the sky. And if something is actually drifting down in frequency, but on a time scale much smaller than your time resolution, you might see it as just a smudge of emission. So that's something to be wary of. But if we observe something that's broadband, and if we observe something that's downward drifting subburst, that's hard to mimic due to instrumental effects. So we think that these 2 other archetypes, they might be caused by the instrument, but actually represent different morphology. But there's these clear cases of the broadband burst and the downward drifting subburst. And the interesting thing is the broadband burst seem to be mostly associated with non-repeaters, in the sense that we have not yet seen any bursts from repeating sources that look like this. And on the other hand, you have the downward drifting subbursts that seem ubiquitous among repeating sources. Although we also see some bursts that appear to be drifting, for which we haven't yet detected a repeat burst. So this is just by looking at all the dynamic spectra, you can make this kind of inference, but we would like to quantify the difference. And so what we do in the catalog is we do burst modeling. So here I'm illustrating this where you have frequency over time. Burst can have multiple components, which I illustrated here with gray ellipses. And for every FRB, we assign one dispersion measure, one scatter broadening timescale, and they can have different frequency and time centers. And then the widths are just Gaussians in time. And then the way we model the spectra is with this running power law, which I put the mathematical formula for here. But important to note is this running power law, it can both model the broadband bursts that have power law-like spectra, and it can model the narrowband bursts that have more Gaussian-like spectra. You can see this if you, if the running goes to 0, you just recover a power law spectrum like you used to with the spectral index. But if the running is very negative, the if you would plot this function, it looks like a Gaussian and approaches a Gaussian very well. So we apply this modeling to all of those 500 or so bursts in the catalog. And then, as you can see here, we can model both bursts that have this power law-like spectrum, for example, for this burst on the left, and also model bursts as the one on the right, where you see multiple components and a Gaussian-like spectrum. So we get these numbers for all of the bursts, and then we can compare the full sample of bursts, and you get something like this. So there's a lot to unpack here. What I'm showing is the spectral running to parameterize the spectra of the burst on the vertical axis. So if the spectral running is close to 0, Gaussian-like spectrum. And this is the intrinsic width, so it's the fitted width of the burst, taking out dispersion, smearing, etc. And then the different colors here in blue are all the one-off events, so the ones that haven't yet repeated, and then in orange and in green are the repeater bursts. And I'm showing the green burst, those are just the first repeater detections to avoid being biased by subsequent detections. And then these are the smoothed 1D histograms, and you can see in the 1D histograms that the distributions of one-off events is different than the distribution of repeater bursts. And we can also test this statistically, and it turns out this is statistically significant. So what we can tell from this is that repeaters on average have longer durations and narrower bandwidths than one-off events, which is very interesting. It's something that we already thought was happening, but now you can actually quantify it. It might be a little bit more intuitive to look at it like this. So here I'm showing not the spectral running of the fitted spectra and not the fitted width, but I'm showing just the duration and the bandwidth, which you can basically eyeball when you first see a dynamic spectrum. And now here in blue are all the one-off events, and in red are the repeater bursts with their one-dimensional histograms on the side. And then if you smooth the distribution separately, you can clearly see that they are different distributions here in blue, the one-off events, and in red, the repeater bursts. So this is very interesting. They seem to have different distributions, and this also has potential for creating a predictive classifier for the first time. So say you detect a new burst, and based on its duration and bandwidth, you can at least probabilistically say, oh, this might well be a repeater, or this is very unlikely to repeat. And that can help you plan follow-up observations, for example. So we don't think this is caused by any instrumental effects. We think the difference is real, although instrumental effects definitely does smear out the distributions a little bit. So the question then is, what causes this observed width and bandwidth difference? It might be intrinsic, maybe the emission mechanism of repeater sources and of one of FRBs is slightly different. It might also be a propagation effect. Maybe it's related to this periodic activity. It might be due to plasma lensing that might preferentially play a role in one of the two populations. And there's also this idea by Liam Connor and collaborators that it might be related to beaming geometry, where FRBs that repeat have wider opening angles. Although that doesn't yet explain the bandwidth difference, just the width difference. And of course, eventually we'll have to combine this morphological information with the rotation measures of these sources, polarization information, and also the host galaxies. Yeah, so another question we asked ourselves in the catalog is, we had these bursts from repeating sources. This is from the periodically active FRB 2018-09-16b. This is one burst. And you see these were detected by CHIME. You have two subbursts. This one seems to be drifting upwards, but the time difference between these two components is 60 milliseconds. So you run into this issue of, are these really two FRBs, or do we say this is one FRB under one burst envelope? Because we do the modeling of all the bursts in the catalog, we get these centroids of every emission component or every subburst, which gives us a subburst separation in time and a delta nu or subburst separation in frequency. And then if you consider all of these bursts together, so here I'm only showing bursts for which we have 2 or more components, because otherwise the separation is undefined. Again, in blue are the one-off events, and then in orange are the repeater bursts. So let me walk you through this. I think the most interesting part is if you look at the subburst separation and time histogram here on the top, you don't really see a bimodality on this time scale and with this number of bursts. What I mean by this is like the burst on the previous slide, that's 60 milliseconds apart. There doesn't seem to be a clear transition from which we can say, oh, this is where we start calling things 2 bursts, and then this is where there's still 1 FRB. And really, if you would extend this figure and look at the nearest separation of 2 repeater bursts after this time scale, I think it's only it's a few minutes. So this is not really conclusive. Then you see this cluster of repeater bursts here that all have negative delta nu, so a negative separation in peak frequencies of the emission components, which we already knew they're mostly downward drifting. And then a lot of these blue points, one-off events, might be repeaters that we haven't yet identified as repeating sources. And now there's some apparent upward drifting burst here, but I think that's due to modeling uncertainties. These are the waterfall plots for these events. I think here it's just very uncertain what you would call the peak frequency of the emission. So I would say these are consistent with not drifting at all. And then the other thing on this figure is here's the galactic magnetar burst that we detected with CHIME FRB, which you can see the waterfall plot of here. So this seems to be unlike any of the other bursts that we detected with CHIME FRB, although I have to note here that the signal to noise of this event was very, very high in comparison to most of the events. So it might not be the best comparison. So one of the interesting aspects of FRBs is using them as astrophysical tools for studying cosmology and the interstellar medium and intergalactic medium. From studying the morphology, actually what I want to say is we need to learn about morphology to understand FRBs as tools, because for example, for these bursts that consist of multiple components, there's some ambiguity in the number of components, the dispersion delay, and the scattering timescale. So we have to study in detail how well do we need to know the dispersion delay and the scattering timescale for typical applications, and do we get into trouble if we want to use these very complex bursts for this application. On the other hand, another potential use of FRBs is for detecting gravitational lensing. And in this case, the complex structure of the burst might actually help us identify copies of each other. Because if all bursts just look like this simple delta function, then everything looks the same on the sky. But if something has complex structure and you see another one of the same complex structure, that might be a hint that you're looking at a lensed candidate. So these are just some things to think about going forward. And another sign that we really need to understand burst morphology of FRBs to also use them as tools. Finally, some of the limitations of the study is we only look at the burst morphology in intensity data at 1 millisecond time resolution, and somewhere where we say this is one component at 1 millisecond might, if you zoom in on the burst at higher time resolution, really turn out to be 2 components of more components. And so we really need to map out the distribution of burst widths and bandwidths of FRBs at higher time resolution of microseconds. So this is something we can do with CHIME FRB baseband data, so the complex voltages of the telescope that we dump on detection for a lot of bursts, but that are not part of the catalog yet. And here are some more examples from the literature of high time resolution study of one-off events and repeater bursts. And so far, they've mostly been done on individual sources, but we are moving towards being able to do this also on larger samples of bursts, by which we can fully map out the distribution. To summarize, we're working on the first CHIME FRB catalog. It's in preparation. If we look at the one-off events and compare them to the repeater bursts in this catalog, they have different observed width and bandwidth distribution, and it's unclear if that's an intrinsic effect or if it's due to some propagation effect. When studying the morphology with CHIME FRB intensity data, we have to be wary of instrumental biases, but we think we understand a lot of the important biases. And going forward, we have to look out for high time resolution studies of burst morphology. Thank you.
Thank you very much, Ziggy. I'll clap for you. Sorry, it's a bit sad. I'm sitting here alone at the Institute and I'm clapping alone as well, but I'm sure others are as well. We have a question from SALF-VII. Hopefully the questions are now visible to everyone as well. And Sander asks, what is the probability so far one-off FRBs and the lower part of the plot are repeaters? Do you think it's worth following them up?
So not all of them. There's more paths of inquiry that you can take. So one other aspect of this is the exposure to sources. So a lot of the high declination sources we had a lot of exposure to with CHIME, but some of the lower declination sources we had low exposure. So these are more interesting to follow up because we might just not have the chance to find a repeat burst yet.
Yeah.
And then there's also here another limitation of the study is we only study the highest signal to noise beam detection, but for a lot of the detections, we have information from surrounding beams that can tell us also something about the spectra of the sources. So if you do a little bit of a deeper dive, we can select the sources that are potentially most interesting for follow-up.
We have time for more questions, so I encourage people to add them to the Q&A. While we're waiting for that, let me ask a quick question. So you mentioned that most of the bursts are drifting down in frequency, but every once in a while it seems like there's maybe like a drift up. But at what level could that just be closely spaced separate bursts that where the second burst that happens maybe shortly after the first one is also then just drifting down, that it starts at a higher frequency?
Yeah, so maybe that was not clear enough, but that was what we were trying to answer with this looking at this distribution. We were hoping that if you look at the subburst separations and look at this histogram, that there would be some clear bimodality, and say if we draw a line here at maybe 30 milliseconds, everything to the left we call that 1 FRB, everything to the right we call that 2 FRBs.
Yeah. Okay.
But it's not so clear with just these 500 bursts where to draw the line.
Okay, we have Philippe Zarka says we have a paper. He would like to elaborate for 1 minute. Let me just very quickly let Philippe unmute. So Philippe, you should be able to talk now.
Yeah, can you hear me?
Yeah.
Yeah, thank you, Jason. Well, of course, it's one of the 50 theories that have been proposed, but we like this one because it's based on the first paper in 2014, and now the sequel has been just accepted in Astronomy and Astrophysics. It's based on pulsar companions. And the companions in the first paper was possibly a planet. Now we are looking for asteroids. And it turns out that companions, not companions that fall onto the pulsar, that's not it. Companions in the wind that provoke and that create an Alven wing, what is called an electrodynamic interaction, and a focused emission in this wing. And in this paper, we can explain both non-repeaters and repeaters, and the bursts that are very close together are attributed to turbulence in the wind. So check it out.
Thanks. I'll make sure to read that.
Thanks, Philippe. All right, now we are at the end of question time, and we're a few minutes behind, actually. So the remaining questions, maybe you can answer them. It's possible for you to answer them in the Q&A as well, Ziggy. You can type an answer. Yeah. All right, thank you very much. Clapping again, Mark Kuyak is telling me that I should be having a canned audience applause thing going. I don't have that ready. Our next speaker is going to be Pratik Kumar.
Yeah, I think everything should be working.
Yeah, looks good. And Pratik's going to be talking about pulsar monitoring with the long wavelength array to measure interstellar effects. So you also have 17 minutes plus 3 minutes for questions, Pratik.
Okay. Yeah, so I'll be talking about some of the pulsar monitoring work we have been doing with the long wavelength array. To start off, a brief introduction about the long wavelength array. So a long wavelength array is a low frequency instrument operating between 3 and 88 megahertz. Currently, there are 2 stations in New Mexico, LWA-1 and LWA-Seviera. LWA-1 is located with the VLA, and LW Seviera is about 75 kilometers away from the first station. Both stations have 256 dual polarization dipoles, which is arranged in a 100 by 110 meter ellipse. And they primarily operate in two modes, beamforming and all-sky imaging mode. There's also a planned construction of a mini station at the north arm of the VLA next year. And apart from this, there is also the overall LWA station, which is now a super station and has been recently upgraded, which I guess you'll hear about more in the coming days. But the plan going forward is obviously to build a swarm where you have a number of mini stations across the US acting together, which will provide arc-second resolution for imaging. And then in terms of pulsars, you can think of this being interesting to study things like pulsar scattering, trying to resolve pulsar scattering. So this map here shows in blue the current stations and red potential future stations across the US. So moving on to the monitoring program. So a significant part of the observing at LWA1 is dedicated to pulsar monitoring, since pulsars are steep spectrum sources and they are easily detected at low frequencies. So pulsar observations began in early 2013 at LWA1, and the monitoring program began in September of 2015. The current monitoring program has 108 sources, which includes 98 pulsars, 7 millisecond pulsars, and 3 rotating radio transients. And this figure here shows the distribution of those sources on the sky. Now, since we have a large number of sources, the observing is also done in an automated fashion using a Python-based script, which schedules these sources at a cadence of about 3 weeks on the station during the times when there is no other projects scheduled. So these are observed as filler projects on the stations. The observing primarily happens at 4 different frequencies: 35.1, 49.8, and 64.5, and 79.2 megahertz, each with a full bandwidth of 19.6 megahertz. After the data reduction step, there is also a data product which provides the continuous coverage from the lowest to the highest frequencies. So moving on to the data reduction part. So once the data has been observed, it's stored on the LWA user compute facility, and then is reduced using an automated data reduction pipeline, which uses a combination of softwares from the LWA software library, which are tools for reducing data for specific to LWA, and then other standard pulsar softwares like Presto, Tempo, etc. And so the pipeline is available on GitHub. Here's the link and a snapshot of how it looks like. And once the data has been reduced, all the reduced data products are also stored on an archive for anyone interested in doing pulsar-related research. Currently, the archive hosts about more than 400 beam hours of observed and reduced data. And then here's a link for the archive, and then again a snapshot of how that looks. So this is all publicly available. So moving on to one of the projects. So pulsars are sensitive to changes in the interstellar medium. An example of that we can think about is the dispersion measure of the pulsar, which is the line of sight integrated electron density. And this is sensitive to changes in the structure, sensitive to changes in the ISM structure, and things like motion of the pulsar through the ISM. So as the pulsar moves through the ISM, your line of sight changes. And so you're now seeing a different part of the interstellar medium. And then it's also affected by things like external factors, such as solar winds. So better understand these effects, we monitor a set of millisecond pulsars, which are more sensitive to these variations because of their smaller periods. And then for these pulsars, on top of the normal monitoring program at the 3-week cadence, we also do a set of dedicated campaigns during the solar minimum. So this is when the pulsar is at the closest approach to the sun, and so that we can better understand the effect of solar wind on the pulsar. An added application of this is to provide better estimates for these DM corrections for high frequency pulsar timing array data, which aim to detect nanohertz gravitational waves. And one of the largest source of noise in the data is the time variable component of the interstellar medium. So very briefly about how the analysis works we take all the data that is available from the monitoring and the solar campaigns at 3 different frequencies, 49.8, 64.5, and 79.2 megahertz, with the full bandwidth of 90.6 megahertz. And then we choose a set of best profiles from those, which are far from the sun, at times when the pulsar is far from the sun, so that you avoid any contamination to the profile, zap any possible RFI, and then add them all together to build a significantly high signal to noise profile, and then model it as a Gaussian, which we then later use as a template. And then all the data is also zapped for RFI, followed by creating one sub-integration and 8-channel archive file, which can be 2 channels for weaker pulsars. Once we have all these things, we use the templates and the data to derive the time of arrival using PS archive, and then fit the models using tempo. So moving on to the first millisecond pulsar, J2145-0750. Here I'm showing you the variation of DM over time. So on the left vertical axis, we have the DM offset. And on the right vertical axis, we have solar distance, which is the distance between the pulsar and sun in angular scales. And the horizontal axis is the time axis. So you can see these spikes in the DMX values during the times when the pulsar gets close to the sun, clearly showing the effect of solar wind on the pulsar. And then if you ignore those spikes, then you also see a slow time varying component, which can be an added effect of solar wind as well as the interstellar medium for this pulsar. Now, if you plot the DMX against solar distance, again, you see a sharp sort of cutoff in the DMX values at a distance of about 25 degrees, indicating that solar wind effects become really prominent below these distances. So for the next pulsar, we have J0030 plus 0451. Again, you see there are strong trends in the DMX value during the closest approach to the sun, like these points here. And then there's a smaller drift in time of the baseline component, as if you can see, for this pulsar compared to the previous one. Again, if you plot the DMX values against solar distance, you see the similar trend as J2145, where there's a sort of cutoff at around 25 degrees, and the value starts to rise up as you get close to the sun. The next one is J0034-0534. Now, there are 2 different things in this case. There's a small time varying component at the baseline here, which is also drifting downwards. And on top of that, you have these trends due to the solar winds. Now, it may not be very evident in this plot, but we see these solar wind effects to much larger distances. So in the previous case, you were seeing strong trends to about 25 degrees. Here, these things are visible to about 40 or 50 degrees. And the fact that this is the fastest pulsar in the sample, so this is most sensitive to changes in the DN. And so you see those effects more profoundly at larger distances. And then for this slow drift in time downwards, we also detect a small change in the proper motion of the pulsar. And so the idea is that as the pulsar is moving through the interstellar medium, you're seeing a different part of the ISM, and so your DM is changing by a small amount over time. The next pulsar is J1400-1431. Now, again, here there are two significant trends here. You have a strong DM offset going upwards in time, and sitting on top of that is your solar wind effects. So the solar wind effects are similar to what we have seen in the previous pulsar, but for this strong drift upwards in time, we don't know what exactly is the reason. We are still looking into it as of now, but this is a fairly recent millisecond pulsar, and so we started observing it right after it was discovered. And so, although we have detected slight improvements in the binary parameters for this pulsar and other parameters, but it's unlikely. It's not. We are not really sure that this trend is due to that. It's possible that this is due to some effects in the local interstellar medium. So this is a very close pulsar with a DM of about 5. So it's possible that there are effects in the local interstellar medium which is making these changes in the pulsar dispersion measure. So finally, to summarize things, we see that low frequency monitoring of pulsars are interesting to study interstellar effects and things like solar wind. In particular, we see that solar wind effects on the dispersion measure becomes significant at distances smaller than about 25 degrees between the pulsar and the sun. And moving forward, the idea of doing this is to actually provide some useful information for the high frequency pulsar timing observations so that they can improve their sensitivity to gravitational wave detection by reducing the noise from the time varying interstellar component. And also this can be used to improve the existing solar wind models. So the next step of this work is what we want to do is actually apply these DM corrections to existing PDA data and see what kind of improvements that yields. Now, what I have talked about so far is only a small fraction of the data with the LWA pulsar monitoring and a very small part of the project. But in principle, there's a ton of data available for a lot of different sources, and we have plans to look at other things for them. The idea is to look for profile variations in time, which could also potentially reveal presence of any off-pulse components related to any structures in the interstellar medium. These long-term profiles can also show us more changing in any pulsar if there is. And then to look at the variations in rotation measure and DM for not just these, but other pulsars as well. But these are only some of the ideas, and it's not really limited to doing the science with these. It's only up to what people can think of doing with the data. Okay, thank you.
Thank you very much. I'm going to try something new. I'm going to try playing some canned applause.
Oh, that's cool.
There you go. All right. I think we have some questions from Pratik for Pratik. Katerina Tiburzi, would you like to ask some questions verbally?
Sure. Thanks for having me. Hi. I can hear a terrible echo. So okay.
Pratik, can you mute while Katerina is asking her question?
Oh, sure. I guess I have to stop share for a moment.
Yeah, okay. So it's a really nice work. I'm particularly interested in this because I'm doing something very similar with Lothar and Nenufar, along with some other colleagues and Jean-Matthias. So well, one of my questions I think has been already answered with your last slide. So it was up to which solar elongation you can see DM variations from the sun. I understood it's more or less 25 degrees. Am I correct?
Yeah, that's correct.
Okay. And my other question is, you mentioned that you are producing a template by modeling, let's say, I guess an average of the observations outside the solar conjunction with the Gaussian, but I haven't understood if you're modeling them with the sum of Gaussians or with an individual Gaussian.
Yeah, so we model with a sum of Gaussians, but usually there is only one component in there.
All right, thanks. That's all I have.
Thanks for your questions, Katerina. There's also a short question from Jean-Matthias Griesmeyer asking what is DMX? What is this parameter that you're fitting?
So DMX is the offset from the reported DM for the pulsar. So whatever time excess DM or lower DM you might record in time.
Yeah, so you have some fiducial dispersion measure that you compare to.
Yeah.
Okay. Are there any other questions for Pratik? I'm just checking quickly. No, if not, thanks again, Pratik, for a very nice talk. And we'll move to Emmanuel. So our next speaker is Emmanuel Fonseca.
Jason, can you hear me?
We can, yes, or I can at least.
Thank you very much.
And Emmanuel is going to be talking about high cadence timing observations of radio pulsars using CHIME. I'll let you know. Yeah, you have 17 minutes as well, Emmanuel.
Perfect. Sounds good. Thanks, Jason. And thanks everyone for attending and to the organizers for giving me this opportunity. Truly appreciated. And thanks to the people who spoke before me. Great talks. Thanks, Pratik, and looking forward to the remaining talks. So I would like to share with you all some updates with regards to enabling the CHIME telescope, which you heard some talks back, to not just be an FRB observatory and not only have it do its cosmology measurements, but also have it be an instrument for pulsar astronomy in general. So, oh, fine, there you go. So for those who are not familiar, CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. It's this wide field, low frequency radio interferometer. And the idea, as was mentioned some talks back, is that in the course of designing the experiment in general, it was realized that the time resolution, the frequency resolution, and the wide field nature of the instrument was really conducive for lots of science beyond cosmology, particularly in the radio transient cases. And Pragachala and Zigipunis beautifully spoke about the FRB case. And in this talk, I'm going to focus on one of the other many science cases that CHIME is working towards at the moment, specifically studying radio pulsars, which Pratik nicely discussed just before I began talking. So for those who normally do not think about radio pulsars or just are not as familiar, this is the basic schematic we tend to have in our minds when talking about them. Pulsars are rotating neutron stars. For reasons we don't fully understand, they emit beamed radiation along their magnetic poles. And if the orientation is just right, we'll observe these neutron stars, these rotating neutron stars, as pulses in the distance, as cosmic lighthouses, so to speak. Nonetheless, neutron stars are physically very extreme. They have as much mass as the sun, but their physical scales of neutron stars are comparable to that of major cities on the order of 10 to 15 kilometers, say. So everything, the gravitation, the electrodynamics, nuclear astrophysics, the interior to the neutron star, all those things are really at their most extreme, as close as you can get in terms of extremity without these things being black holes. So in that sense, radio pulsars are quite sought after in terms of trying to open or address a lot of these open questions on what's typically called fundamental physics, because of the kinds of environments you tend to access by observing them. And the key technique that we use, at least in the radio pulsar side for studying pulsars, is called pulsar timing. Conceptually, it's just you measure the arrival time at which you see a pulse at your observatory. You repeat that measurement for many different pulses collected over time. And then you just try to reconcile a bunch of timing-based phenomena that you see in that timing data set. And that's basically pulsar timing in a very, very brief nutshell. Nonetheless, though, when it comes to what we can achieve in practice, for many sources that we know of in our galaxy, pulsar sources rather, the timing can be so great so as to be on the order of sub-microseconds, if not tens of nanoseconds. And with that timing precision, you can actually access a vast landscape of applications and areas of study. And I only list a small subset here, ones that I'm quite partial to. But if you're interested in gravity, nuclear astrophysics, gravitational wave astronomy, astrometry, what have you, Pratik very beautifully discussed ISM physics, all those sorts of things you can probe pretty directly, quite directly with pulsar timing in general. So with that, all those sorts of opportunities very much motivated the construction of a backend for CHIME that would actually be conducive for pulsar observations. So over the past few years or so, a bunch of us, some of whom are in the audience, and I'm speaking on their behalf, we designed, built, and implemented this, what we call the CHIME Pulsar backend. It's a 10 computing node cluster. Each of these 10 nodes are fitted with an NVIDIA GPU that's used for the real-time manipulation of data that's conducive for pulsar astronomy in general, specifically pulsar timing, though not only pulsar timing, as I'll show in a few minutes. And again, in terms of real-time manipulation, the raw tide array beam baseband that we receive from the CHIME correlator in real time is coherently chunked together and averaged to form slightly higher signal-to-noise pulse profiles from the original raw baseband time resolution, but also coherently de-dispersed so as to remove the effects of the ISM on the pulsar data we get with CHIME. And that's really key when it comes to trying to achieve really high timing precision results that you need for if you want to, for example, detect gravitational radiation and so on. So in that sense, the CHIME Pulsar backend, despite being slightly different in terms of number of compute nodes and so on, fundamentally operates the same way as other backends do at, say, the Green Bank Observatory or observatories in Europe and so on. The data products that are output from the CHIME Pulsar backend are very much the kind that you get elsewhere. But there are two logistical differences that make it quite unique. And one of which I focus on here is that the CHIME system, the CHIME correlator and the CHIME Pulsar backend are able to be controlled and work together such that the CHIME correlator produces 10 tide array beams, each one tracking a different celestial position. And the CHIME Pulsar backend with its 10 compute nodes are able to receive all those data for those 10 different streams of tide array beam baseband and actually process those data in tandem. So in that sense, we're able to look at 10 different sources instantaneously with the CHIME Pulsar backend. And that's one of two key things that make it quite different from backends at other observatories. Again, we can track up to 10 sources at any instant in time, but because of that automatically controlled flow of scheduling sources, of forming beams, and so on, we're able to really optimize the number of sources we can look at, modulo user-defined priorities, say, for sources that are physically interesting or for which high cadence observations are desired. And with that, because of the design of CHIME in general, the fact that the CHIME correlator, so long as the on switch is on, will constantly be generating data for all of its science cases, the CHIME Pulsar backend normally acquires timing data on 400 to 500 sources per day, so long as the correlator is operational. So in terms of what these data look like, again, the kind of data that the CHIME Pulsar backend produces fundamentally is no different from what's produced elsewhere, just at a different frequency range and a different observatory, of course. On the left is shown a time series of what we call our fold mode, basically, where, again, as I mentioned before, the real-time tide array beam baseband is manipulated, it's chunked up and folded together to produce slightly higher signal-to-noise profiles, each of which are stacked here for this source 1937 plus 21. It's a very famous millisecond pulsar, one of the most precisely timed ones out there so far. And on the left, we just show a typical transit of this source at the CHIME in the CHIME field of view. You see that as it drifts in, you'll start to see the profiles, and as it transits, it's at maximum brightness, and as it fades out, it weakens. Because again, CHIME is a static interferometer. The sky does the moving, and CHIME just sits there and looks straight up. And on the right, for the same data set, we're able to form other products such as time average dynamic spectra, as shown here on the right. And in general, we acquire data for all 4 elements of the Stokes polarization vector. And because of that, we actually obtain as much data as possible that enable all sorts of different scientific studies. Again, if you're interested in timing, polarization properties, flux density measurements in general, the kinds of data that the CHIME Pulsar backend is taking and putting out is very much the same as those you get elsewhere. And the other mode that we typically observe in is what's called the filter bank mode. And this is just a slightly downsampled in time series, which is highly conducive for studies of single pulses from known sources, whether they be galactic or extragalactic. In fact, this is very much the mode that FRBs are searched for and found in. And in fact, CHIME Pulsar made an early appearance in the literature because one of the 5 detections that was made of the second known repeating FRB that was discovered by CHIME FRB, we followed that up with the CHIME Pulsar instrument during a mode of our period of commissioning the CHIME Pulsar instrument. And we were able to detect several bursts from this source with the CHIME Pulsar backend too. And I highlight the detection that was shown in the paper here. So in terms of the performance of the backend, like I said, it's very much designed and implemented so that we have this priority-based scheduling such that it optimizes the number of sources that we get and the cadences with which those sources are observed. And on the right is shown histograms of the sources that we do observe over a 60-day period of time. The 2 histograms basically just show sources that are observed within the right ascension range of 18 to 20 hours. And on the bottom is the same plot, but for all other sources, for sources that are outside of that galactic plane time, so to speak. And you can get a sense of how sources are scheduled and how often they're scheduled too, because there are just so many sources within that small 2-hour period of time. And there are far fewer sources, but nonetheless, with the statistics we have in hand and the way in which things are designed, we're still able to observe basically all but 14 of the nearly 1,200 pulsars in the Northern Hemisphere are in the field of view of CHIME. And these 14 are not being observed largely just because of limitations we're hitting limitations in the way in which we can prioritize sources to be scheduled, because there are quite a few sources that are requested to be looked at every single day for all sorts of purposes. And so there is some wall that we hit there, but nonetheless, we can shift things around so that all sources can be looked at with some cadence, whether it be 1 day in duration or months or so. Again, because we record not just full Stokes, not just total intensity, but full Stokes information, so polarization information as well, we are able to obtain nice polarization profiles of all the sources that we look at, especially when we look at sources in the fold mode of the CHIME Pulsar backend. And on the right here is showing examples of the polarization profiles we achieved for the same source I showed before, 1937. And one of the major questions with any experiment is calibration. How well can you calibrate your data, and how well does those calibrated data match up with what you'd expect and what you see with other instruments? And as you can probably imagine, with an instrument like CHIME, which has this half cylindrical structure, calibration is quite complicated. Nonetheless, we're able to achieve relative calibration accuracies on the order of % that are actually quite stable in time. So the data we acquire on 1 day and then some days later or a year later generally have the same properties, which are, however basic that may seem, is important for a new instrument that only just hit the ground running within the last year or so. Finally, again, because this is a timing instrument, you would probably figure or ask even, how good is CHIME at when it comes to observing pulsars and timing pulsars? And what this figure shows you here is a summary plot of timing residuals. So that's the statistic you can derive when you fit a model to data, and then you just take the difference of the data and the model of that data, right? So, so you would expect if the model's good that the residuals would be hovering around 0. As you can see here is indeed the case for this source that's actually observed by the nanograv collaboration, which is seeking to detect gravitational waves with nanohertz frequencies. And the data sets shown here, the dark blue is the data we've acquired with CHIME, and the bottom panel is the same as the top, but just focusing only on the CHIME data set, so zoomed in essentially. And these data points, these orange and light blue points here on the left, are data for the same pulsar, but acquired with the Green Bank telescope using the Guppy instrument. And these are data acquired under the Nanograv Observing Program that was recently released for their 12.5-year public data release. And as you can see, when you combine data taken with GBT and CHIME, the combination works well. The model is statistically adequate and statistically consistent with previously published models. And even the statistics of the individual data sets match up quite nicely, as you can see here on the right, when looking at the normalized, the distribution of normalized TOAs as weighted by their uncertainties. So in that sense, we very much are able to produce these data sets that have statistical properties consistent with those we see elsewhere, and desirable for all sorts of high precision studies. So over the last year or so, there's been several population-based studies that use CHIME Pulsar data. And the nice thing about CHIME Pulsar in general is that, again, because it's designed to optimize the number of sources we see on any given day, and even just in general over small periods of time, we really are tapping into a largely untouched population, or at least a population that's hard to assess, given that many other observatories have naturally limited and competitive resources. With CHIME and CHIME Pulsar, we can access the sky and look at as many sources as we can, so as to really improve the measures that we can generate from the population. And an example is shown here on the right. Postdoc Young and company were able to measure nearly 60 new rotation measures, so polarization rotation measures, which reflect the degrees of the parallel components of the magnetic field in the galaxy, for again, nearly 60 new sources, and they refined rotation measures that were previously known, but for another 25 new sources, with only a year of data, right? So these sorts of projects would take quite a long time, and it would require lots of telescope time, because CHIME Pulsar is naturally suited for generating these large, high cadence data sets from many sources. We're able to turn around those things quite nicely and generate these maps, for example, of rotation measurements in various parts of the galaxies. So in that sense, CHIME Pulsar is really good for a lot of these large-scale statistical population-based studies. And in general, too, the CHIME instrument is just quite a sensitive monitor of single pulses. And both Pragya and Ziggy very beautifully summarize that for the FRB side of things in terms of its untargeted searching of FRBs. But we're also sensitive to single pulses from our own galaxy. And it turns out that there's just lots of erratic sources in the radio sky as observed with CHIME. And to date, we've found at least 20 new galactic sources, many of which fall under the umbrella of pulsars, or what are often called rotating radio transients. And we actually keep a running list of these sources that we find at this URL, which is commonly done for other pulsar search surveys. And I just would encourage people to keep an eye out for lots of really cool student-led projects that are going to come out over the next few months or years. So some of which led by Deborah Good, Bridget Anderson, Adam Dong, and company, regarding these sorts of discoveries. But again, beyond the yes.
Yeah, about 1 more minute.
Perfect. So beyond the population-based studies and just discovering new sources, looking at long-known sources is actually quite fruitful as well, because we are able to hammer these sources pretty frequently, and we're able to just generate these high-density, high-cadence data sets. An example of which is shown here for a millisecond pulsar 0218 plus 4232, discovered in the mid-late 90s, actively studied for a very long period of time. And here I just show a 1.5 years worth of data we've acquired with CHIME Pulsar. On the left is showing the time series of the dispersion measure, or DM over time, specifically the DMX that Pratik nicely described in his previous talk. And with this 1.5 year long data set, we actually already are sensitive to all sorts of effects that would normally take many years to resolve, just because you need high density data sets. And an example of that is shown on the right, where in this source, in the timing data set for CHIME, we actually are able to detect the relativistic Shapiro time delay, because this source is in a 1-ish day binary system with a white dwarf companion. And despite the source being studied pretty actively with many different telescopes, such an effect has not yet been resolved with those data, largely just due to limitations in sensitivity and integration times and integration and observing cadences in general. With CHIME Pulsar, we see this source every day, and with a 1.5 year data set, we resolve that effect quite nicely. So this will be nicely summarized along with similar detections for a few other long-known sources in a forthcoming study. And with that, I guess I'm out of time, so I'll just leave it here at the last slide. But CHIME Pulsar is generating a high cadence timing data set, and there's lots of things coming from student and postdoc-led studies on that data set, whether it be new discoveries, millisecond pulsar timing, orbital astrophysics, you name it. And along the way, over the last year, we've established partnerships, formalized partnerships with various groups around the globe for sharing of data and resources to enable multi-group, multifaceted science opportunities, some of which are listed here, Nanograv, and as well as Pulsar search collaborations such as P-Alpha and GBNCC. And even recently, we've been in touch with folks in LIGO to enable their untargeted or targeted searches of gravitational wave signals from galactic sources. So there's lots of things happening on the Pulsar front too with CHIME, and encourage you to just keep an eye and ear out for sure. So stay tuned. Thank you.
All right, thank you very much, Emmanuel. Maybe I'll ask a first question. I see Deborah Good has a comment. Maybe Deborah, if you don't mind, maybe you want to say for 1 minute, provide more detail on your comment. Maybe I can ask a quick question, Emmanuel. So there are 19 discoveries so far. I guess on each part of the sky, you have something like, I don't know, 20, maybe maybe 20 hours per year on each position on the sky or something like that. Is it already becoming clear what fraction of pulsars are kind of dominated by very sporadic individual pulses as opposed to being more persistent sources?
Yeah, it's a good question. I mean, the studies that I was referring to, and I think the one that Deborah will briefly talk about, I mean, we're definitely starting to gear towards trying to get a sense of the behavior of sources, that we know about, and trying to get these sorts of statistical analyses of, intermittency, or in terms of like bright or giant pulses versus ones that are more constantly, at some brightness or activity. And then trying to relate that to the discoveries we make, right? Because it's a good question to try to extrapolate upwards and say, with an instrument like CHIME, how many sources could we truly detect? So it's a good question. That's very much something we're pondering over and trying to address ourselves.
Yeah, I'll just jump in since this is kind of my baby. But so our first paper, which is coming out hopefully this week, is submitted hopefully this week, is 7 new sources. And it's with N of 7, it's hard to say much statistically. There's also all kinds of selection effect problems versus, within CHIME, and then also CHIME versus other instruments that have detected rats and pulsars. So our conclusion for right now is that we can't really say that much about the rat or intermittent pulsar population. However, I would say that what we are seeing is that as we continue to study more, both discovering more sources, but also doing more systematic studies of known intermittent and rat-like things, I think this is going to be a really powerful program for understanding those kind of questions. We're just a little in the early stages yet, not able to give a great answer right now. But it's pretty fun, and turns out there's actually kind of a lot out there to look at. So,
yeah, that's great. That's very nice that CHIME can do this as well. Also very impressive, like these gravity, GR effects that you can detect with this very high cadence, Emmanuel. Okay. Do we have any other questions?
I could probably ask a super quick one, but I think as a panelist, I can't raise my hand. Emmanuel, very interesting talk. Mine's a little bit side topic, but have you commissioned the circular polarization analysis of these bursts? And I was just thinking, because the sensitivity of CHIME, you're doing all these sky searches, you'd be really sensitive to stellar bursts as well, which would be very interesting. And they'd be more obvious in Stokes-V. But I'm just wondering if you've considered that.
No, so well, currently, at least so for the bursting projects, the ones that tie in both CHIME, the FRB and Pulsar backends together, we're very much dependent on the Stokes-I data set that the FRB backend's producing. So in terms of the searching and so on, at least in terms of alerting of these discoveries, we very much rely on the Stokes-I detections made by the FRB instrument. The nice thing about the Pulsar backend is that when we follow up, we actually could access the full Stokes polarization information. So in that sense, we are able to carry out those studies too. It's an interesting point. I'll definitely bring that up.
And also just like Stokes-V profiles of a large sample of sources is very interesting. Like the largest I know of is like 20 or something odd, and so just knowing what an average profile looks like is very important for differentiating.
Absolutely. That's a great point.
Brown dwarf people.
Totally. Thanks, Joe. That's a great point. Definitely.
We have time for one last quick question. Casey, do you want to unmute and ask it yourself?
Sure, thanks. I was just curious, based on the CHIME FRB presentations, is it true that the rate of FRB discovery is an order of magnitude higher than the rate of discovery of rats and pulsars through the search system?
Yeah, in terms of the statistics I have off the top of my head, that seems largely true. It's funny because the FRB instrument, at least, is largely optimized to try to find extragalactic sources, right? So that, I mean, when we were starting to realize we were finding galactic sources, it kind of occurred to us there was a little bit of psychology in the sense that people were not looking for the low DM sources that would be in our galaxy. So when we started to actually look, we've realized, oh, there's actually lots of sources, right? So in that sense, it's a good question. I don't know the exact answer at the top of my head, but it's something that people are very much working to address.
Yeah, I think it's a super interesting question. You could consider, just what is the average detection rate of a radio pulse from our galaxy versus outside our galaxy? Does volume win over, being further away? Yeah.
Totally.
So it's also a fun psychology question because, we've gone decades without finding FRBs, and now it's all we can find.
Yeah, it's like the pulsar origin, right? Like they were apparently first seen a decade before Jocelyn found them, right? But it takes Jocelyn to find them, right?
It's very hard to make scientific discoveries, right? You need to challenge, what you think is true or not.
Totally.
Great. We need to end here with this talk and move on to our last speaker. So thanks again, Emmanuel, for a very nice talk. To round out this very nice session, we have Sushan Konar, who's going to be our last speaker of this session. Great. Can you share your screen, please?
Yeah, just do that.
Great. And Sushan's going to be talking about the curious case of nulling pulsars, which is related to what was just being discussed. Please
good morning, everybody. Here the date turned to 2nd December just a few minutes ago, so I can say good morning. And I will start by thanking the organizers for an excellent conference and for giving me a chance to speak in this conference. And I should start by thanking my previous speaker, Emmanuel, for giving a primer on radio pulsar and in particular neutron stars. But neutron stars do not come only as radio pulsars. This picture shows you the wide variety of observational classes of neutron stars that we know about. And I would not explain this picture in detail, that eat up into my allotted time entirely. So the different symbols and different colors basically stand for different observational classes of neutron stars. And here in the middle, what you have in the orange color are the radio pulsars. And interestingly, we now sort of understand how to classify this huge diversity of neutron stars. So we basically have them classified according to the mechanism of energy generation, the energy through which we see the neutron stars. So the first is the rotation powered pulsars, and radio pulsars are a class of them, of course, classical radio pulsars, and then you have recycled radio pulsars, the famous millisecond pulsars, and also rotating radio transients. Probably they are part of classical radio pulsars entirely, but for the moment I have kept them separately. And then we have the accretion powered objects, which are neutron stars sitting in X-ray binaries, could have a massive binary companion or a low mass binary companion. And then for want of a better name, we have the internal energy objects, meaning that these neutron stars are shining in whichever frequency band they are shining in because of certain internal processes that are going in. For example, for magnetars, it's the decay of the magnetic field, or for isolated neutron stars, it's the residual heat, and so on and so forth. So what many of us have been doing for many, many years is to find interconnection between these different observational classes. And we sort of understand how the accretion powered objects are connected to the rotation powered pulsars, in the sense that if there is a neutron star sitting with a binary companion, then they would recycle the radio pulsars and they would show up as millisecond radio pulsars or mildly recycled radio pulsars. Whereas we also sort of have started understanding the connection between the internal energy objects, that is the magnetars, with the classical radio pulsars. So there are some indications that probably the difference in magnetothermal evolution connect these objects. But what interests me at the moment is the various subclasses of the classical radio pulsars, which are clubbed together as one set of neutron stars, but they also have different sort of behavior, and which essentially show up as timing hiccups, and the variability in their timing behavior. For example, one particular set of timing variability is the nulling pulsars. Some of the time they just simply disappear. They also have association with the drift of subpulses and the mode changes, and also the spin period derivative changes. And therefore, if the p dot changes, the estimate of the dipolar magnetic field changes. Then, of course, we know about the glitching pulsars, which shows a period glitch, about which I would not discuss at all. So there are these subpopulations: the nulling pulsars, the intermittent pulsars. I'll talk about them a little. The RRATs, the glitching pulsars, and the magnetars. And what are the connections? So perhaps these are the two sets. There are some indication that this set is connected within themselves, and this set is probably connected within themselves. And as we have already heard from Pragya, we probably should also add FRBs here. They are also seem to be connected to magnetars. So here are the basic primer for nulling pulsars. So an ordinary radio pulsars have very regular pulses, whereas for nulling pulsars, some of the pulses are simply missing. And then there are cases of extreme nulling, which we are now calling them as intermediate pulsars, which show up in a few periodic pulses, but then disappear for a very, very long time. And the most extreme behavior is probably shown by the RRATs, which only come in single pulses, sporadic single pulses. Now, the nulling behavior is very different in different pulsars. This is sort of showing the behavior of nulling pulsars. And you see that, I'm sorry, in this particular pulsar, the null happens reasonably frequently, whereas here the null lengths are very, very long. It's mostly not there. And on the other hand, for this particular pulsar, the null lengths are shorter. It's mostly being seen in emission. So there are various nulling patterns that you see, and it changes from pulsar to pulsar. Also, the subpulses drift very significantly in nulling pulsars. And there has also been instances of mode changing. It switching between radio and X-ray brightness has been seen for this particular pulsar. And when the mode changes, sometimes the period derivative also changes. So this is another example of various nulling behavior. And one can also see that the nature of the pulse profile, that also changes between when the pulsar is in emission state and when it is in the nulling state. So the nulling behavior can be summarized as: null is basically an abrupt cessation of pulsed emission, and it is associated with drifting of subpulses, association with mode changes, and it has association with switching emission frequencies and also changing in the spin period derivative. Now, there has been a lot of studies of nulling behavior in individual pulsars. However, there has not been detailed studies on the nature of the population of nulling pulsars, how they behave as a general population, and whether there is something intrinsic about the population of nulling pulsars that make them behave the way they do. Now, in 2017, Vishal Gajjar first made an exhaustive list of nulling pulsars. And last year, we extended that list, and this person, Udipta Deka, who was a summer student, did an extensive trawling of the available literature, and he found all possible nulling pulsars from the literature. And now we have something like about more than 200 nulling pulsars on which one can do certain population studies. So the general characteristics of this population is the spin period is reasonably high. No nulling in millisecond pulsars has yet been seen. So therefore, the magnetic field is also significantly large, 10 to the power 11 to 10 to the power 13 Gauss, and they are reasonably sort of old pulsars, not very young, but not very old either. Now, the characteristic parameters of a nulling pulsar, the characteristics by which people usually sort of describe a nulling pulsar is the nulling fraction, the amount of time it's not emitting. And that ranges from a very few percent to about 95%. The length of the nulling phase. Now, unfortunately, there is not much data in the nulling phase, and it has been seen that neither the nulling length or the nulling fraction is a unique marker for the nulling behavior. As you have seen that there are different ways in which two different pulsars can have the same nulling fraction, but they may be, one may be having very long nulls and the other may be having very short but very frequent nulls.
Sushan?
Yes?
About 5 minutes.
Yeah, sure. So now there are certain particular types of nulling behavior that has allowed us to classify these nulling pulsars. So there are these classical nullers, only a few pulses of emission and few pulses of nulling, and then the intermediate nullers up to a few hours. And intermediate pulsars, they could go on nulling for even years, and we really do not know if it is connected to the RRADs. Now, we looked at the nulling fraction statistics, whatever nulling fraction available in the literature, and this is how it looks, and it looks as if there is a break at the 40% of the nulling fraction. But as you can see from the plot itself that this is not very clear whether we have a break there or not. And we also try to look at the correlation of this nulling fraction with all possible pulsar parameters, for example, spin period, magnetic field, characteristic age, or DM. There doesn't seem to be any pattern anywhere at all. And we have just artificially separated the ones with higher nulling fraction and lower nulling fraction, but it doesn't seem to show us anything at all. So what I would like to go into is a very old concept of nulling pulsars, is that the nulling pulsars are actually very old pulsars. Now, when you say old, that means they're very close to the death line, and we try to figure out how close they are to the death line by defining a parameter, which is the proximity parameter of a particular pulsar. How much time do they have left to reach the death line, divided by the time that they have already spent after birth, that is the characteristic age. Now, when we try to do that, one faces a problem of choosing a particular death line. As you can see, these are all possible death lines that are available in the literature, and these different death lines invoke different magnetic field configurations. Now, here is the most important and interesting thing that we found from our nulling pulsar population is this. all the nulling pulsars, the red circles are the nulling pulsars and the gray dots are all radio pulsars. You see that all the nulling pulsars seem to be bound by one particular kind of death line. And but of course, there's nothing special about this death line. There is this death line and there is another death line, and you see a lot of pulsars active beyond these death lines. And these red stars are very slow pulsars, which are basically functioning beyond all known, all theoretical death lines. But nulling pulsars seem to be bounded by this particular death line. And this particular death line is obtained by using an assumption of an extremely curved field. So does that mean that the nulling pulsars are those pulsars which have extremely curved field, and as they come closer to this death line, they start nulling? Now, this is one theoretical problem which we have started looking at from an observational campaign. Now, how one can look at this problem? Yes?
About 2 minutes.
Yeah, sure. So how one can look at this observational, one can look at this problem observationally is either one has to look at the magnetic field configurations of nulling pulsars, or one has to look at the behavior of the radio pulsar population near this death line. So now magnetic field can be, we only know about, we only assume the magnetic field to be dipolar for radio pulsars, but it has been shown by many people that it actually must have strong multipolar components and much smaller radius of curvature in order to have effective pulsar emission. For example, in this diagram that has been shown that you need such structures in the magnetic field in order to have radio pulsar emission. So therefore, magnetic field is expected to have various kinds of structures. So is what this death line telling us is correct, that nulling pulsars have a particular kind of magnetic field structure? So what we are trying to do with an observational campaign at GMRT is looking at pulsars for their nulling behavior near the death line. And to do that, what we and also trying to understand whether we can study the field configurations of nulling pulsars. Now, we have some interesting indications from our observational data, and we are writing up that paper. It should be out soon. So that is one interesting, exciting result that will be coming up very shortly. And meanwhile, we have this website in which we have made a catalog of all the nulling pulsars. This didn't exist in the community. The community has tables for all sorts of characteristics of neutron stars. Unfortunately, the nulling catalog was not there. So we have made this catalog, and I would request everybody to take a look at the catalog. And if you find one of your favorite nulling pulsar missing, please let me know. We would like to have this catalog available for everybody in the community. So that's where I would like to end. And the people who have been part of the project is I have already mentioned Udita Deka, and my collaborators Bhashwati Bhattacharya and Jayanto Rai, with whom I have initiated a campaign, observational campaign with our upgraded GMRT. And please wait for the results, which would be out soon. Thank you very much.
Thank you, Sushan. Do we have questions for Sushan? Maybe while people are thinking about that, and feel free to put more questions into the Q&A. So I was wondering, you mentioned FRBs as well. I wonder at what level is this phenomenology reflecting basically the magnetic field topology of neutron stars, or maybe whether the magnetic field is being poked and prodded by the influence of external plasma. I mean, are these the kind of knobs that you're thinking of to explain this phenomenology that you've described?
Actually, yes. The internal structure of the magnetic field and just a second, are you talking about the magnetars or the nulling pulsars?
Well, neutron stars in general, actually.
Yeah. So we already know how accretion changes the magnetic field structure, and so that's one kind of physics that we know very well. But the other kind of magnetic field, whether it evolves in a particular fashion in isolated neutron stars, would depend very much on the internal configuration of the magnetic field and the nature of the microphysics of the crust. Now, as you probably are aware of the fact that how the conductivity, the transport properties would be affected because of defects and dislocations in the crust. The new physics is giving us much better handle on the transport properties there. So now those calculations, I would feel that those calculations needed to be redone. These were done long ago, but these calculations are needed to be redone. And also the magnetic field structure in the context of magnetars, we believe that the magnetic field structure could be very different in depending on the initial conditions. So okay. These calculations probably would tell us how whether the behaviors would be totally different. Yes.
Okay, I want to get through just a few other remarks and questions. So Cherry Ing says that CHIME Pulsar has recently published a few more nulling pulsars. Would be great to see them in your nulling database.
Yeah. Actually, I wanted to mention that. I totally forgot because the plots that I have shown, even though they are supposed to be from the paper last year, but I have updated the plots, and they actually include all the nulling pulsars that have been published recently from Cherry Nang and her group.
Okay, there you go, Cherry. Now, Bradley Myers has a question. He says, I'm curious about your thoughts on the connection between rats, intermittent pulsars, and nulling pulsars. It seems to me that the more we find and the deeper we dig, the less distinct these populations become. Perhaps it's not all to do with the magnetic field configuration.
That is possible. That these, I mean, the way I look at it, looking at these pulsars, them being closer to a particular death line, and from there saying that they have a particular magnetic field configuration is one way of looking at it. But there might be many other factors which make them behave differently. So, thanks. Yeah.
And one last quick question to round off the session from SALF-VII. He's asking, are the nulling fraction and nulling length constant or variable over time for a given pulsar?
Actually, in many, quite a few pulsars, it has been seen that the nulling length changes, the phase of nulling changes from time to time. And of course, also the nulling fraction varies depending on how much time you are integrating over.
All right, thank you very much. Thanks again, Sushan. I'll clap on behalf of all of the participants. Thank you very much. This has been a very inspiring session about pulsars and FRBs. We'll end here. I'll stop the recording in a second and sign off for now from Amsterdam. And good wishes to everyone wherever you are in the world right now listening to the session. And a reminder that if you're interested, there's a coffee and tea session right after this that you can join, and the Zoom link is in the materials that you've received. So I'll stop the recording now and end the call. Thank you very much.